Imagine an object so dense, so massive, that nothing, not even light itself, can escape its gravitational pull. An invisible cosmic predator lurking in the depths of space, capable of tearing apart entire stars and warping the very fabric of reality around it. This isn't science fiction or the plot of a Hollywood blockbuster. These cosmic monsters are real. They exist throughout our universe, and they're called black holes. From the remnants of collapsed stars to supermassive giants millions of times heavier than our sun, black holes represent some of the most extreme and mind-bending objects that nature has created. They challenge everything we thought we knew about physics, space, and time itself. Today, we're diving deep into one of the universe's most fascinating and mysterious phenomena, objects so strange that even Albert Einstein initially doubted they could exist. Before we journey into the heart of darkness, if you're captivated by the mysteries of space and want to explore more cosmic wonders, hit that subscribe button and ring the notification bell so you never miss our next adventure through the universe. What exactly is a black hole? At its core, a black hole is remarkably simple to define. It's a region of space where gravity is so intense that nothing can escape once it crosses a boundary called the event horizon. Think of the event horizon as a cosmic point of no return. Cross it, and you're trapped forever. The name black hole is perfectly descriptive because light cannot escape. These objects don't emit or reflect any light, making them appear completely black against the backdrop of space. They're invisible to direct observation, yet their effects on surrounding matter reveal their presence in spectacular ways. At the center of every black hole lies what physicists call a singularity, a point where all the black hole's mass is concentrated. Here, density becomes infinite, and our current understanding of physics breaks down entirely. It's where the known laws of nature cease to function, making singularities among the most puzzling aspects of black holes. The formation story. Black holes form through different processes depending on their type. The most common formation mechanism involves massive stars, those at least 25 times more massive than our sun throughout most of a star's life. An outward pressure from nuclear fusion in its core balances the inward pull of gravity. But eventually, the star exhausts its nuclear fuel. When this happens, the core can no longer support itself against gravity's relentless pull. The core collapses catastrophically, compressing matter to extraordinary densities. If the remaining core mass exceeds about 3 times the mass of the sun, nothing can halt the collapse. The matter continues crushing inward until it forms a black hole, complete with an event horizon marking the boundary from which nothing escapes. This process typically ends with a supernova, a brilliant explosion that blasts the star's outer layers into space, while leaving behind either a neutron star or a black hole. However, recent discoveries have suggested an alternative formation pathway. Scientists have found evidence of what they call direct collapse black holes, where a massive gas cloud simply caves in on itself without the dramatic supernova explosion. This gentler process might explain some puzzling observations about black holes in the early universe. Types of black holes. Not all black holes are created equal. Scientists classify them into 3 main categories based on their mass. Stellar mass black holes are the most common type, with masses ranging from a few times to several tens of times the mass of our Sun. These form from the death of massive stars. Astronomers estimate that our Milky Way galaxy alone might contain as many as 100 million stellar mass black holes, though most remain hidden in the darkness of space. Intermediate mass black holes occupy a mysterious middle ground, weighing between 100 and 10,000 solar masses. These are the least understood type because astronomers have detected very few of them. Recent studies have provided new evidence for these elusive objects, which could hold crucial clues about how the largest black holes came to exist. Supermassive black holes are the giants of the black hole family, containing millions or even billions of times the mass of the Sun. These behemoths lurk at the centers of most large galaxies, including our own Milky Way. Our galaxy's central black hole, Sagittarius A star, weighs roughly 4 million solar masses. Other galaxies host even larger monsters, some reaching tens of billions of solar masses. How supermassive black holes grew so large remains one of astronomy's biggest puzzles. They appear in the early universe surprisingly quickly after the Big Bang, seemingly not having enough time to grow through normal processes. Recent groundbreaking discoveries the past year has brought extraordinary insights into black holes. Astronomers discovered a supermassive black hole feeding at a phenomenal rate, consuming matter over 40 times faster than the theoretical limit, known as the Eddington limit. This black hole, designated LID 568, exists just 1.5 billion years after the Big Bang. Its extreme feeding frenzy might explain how supermassive black holes reached enormous sizes so quickly in the early universe. In February 2024, astronomers found the brightest quasar ever observed, powered by a black hole weighing between 17 and 19 billion solar masses. To maintain its incredible brightness, this monster consumes the equivalent of one sun's worth of material every single day. Perhaps one of the most intriguing discoveries came in 2024 when researchers identified the first ever black hole triple. This system consists of a black hole with two stars orbiting it at vastly different distances, one completing an orbit every 6.5 days, while the other takes 70,000 years. The existence of such a distant companion suggests the black hole formed through direct collapse rather than a violent supernova, which would have ejected such loosely bound objects. Another fascinating discovery involved two massive black holes feeding simultaneously in the same galaxy. One resides at the galaxy's core, while the other, a rogue black hole about 1 million times the Sun's mass, was found thousands of light years from the center. This off-center black hole revealed itself by tearing apart a passing star in what astronomers call a tidal disruption event. Gravitational wave detectors have also revolutionized black hole science. In late 2024, scientists detected two black hole mergers with unusual properties, including one where the larger black hole was spinning opposite to its orbital direction, something never observed before. These observations provide evidence for second-generation black holes that form from previous mergers. How we detect the invisible. Since black holes emit no light, detecting them requires clever indirect methods. When a black hole exists in a binary system with a normal star, it can strip material from its companion. This stolen matter forms an accretion disk, a swirling, superheated disk of gas spiraling toward the event horizon. As matter in the disk accelerates and compresses, it heats to millions of degrees, emitting intense X-rays that telescopes can detect from across the universe. The motion of visible objects also betrays black holes' presence. By carefully tracking how stars orbit invisible points in space, astronomers can calculate the mass concentrated at those locations. This technique revealed Sagittarius A star at our galaxy center and won Andrea Ghez and Reinhard Genzel the 2020 Nobel Prize in Physics. The most dramatic detection method came with gravitational-wave observatories. When black holes spiral together and merge, they create ripples in space-time itself. These gravitational waves travel across the universe at light speed, carrying information about the collision. Since the first detection in 2015, scientists have observed hundreds of these cosmic crashes, each providing unique insights into black hole properties. In 2019 and 2022, the Event Horizon Telescope collaboration achieved what many thought impossible, directly imaging the shadow of a black hole's event horizon. Using radio telescopes spread across the globe to create an Earth-sized virtual telescope, they captured images of the supermassive black holes in galaxies M87 and our own Milky Way. These images show bright rings of light from the accretion disk surrounding a dark central region, the black hole's shadow. The strange physics of black holes. Black holes create some of the most extreme conditions in the universe. Near the event horizon, time itself behaves strangely. Due to gravitational time dilation predicted by Einstein's general relativity, time passes slower in strong gravitational fields. For an outside observer, anything falling toward a black hole appears to slow down dramatically, taking infinite time to actually cross the event horizon. Yet for the falling object, the journey takes only a finite time. Black holes also produce powerful jets, narrow beams of particles shooting away from the poles at nearly light speed. Recent observations of Sagittarius A star hint that our galaxy's supermassive black hole might harbor a hidden jet, similar to those seen in other galaxies. These jets can extend for hundreds of thousands of light years, profoundly influencing their host galaxy's evolution. Theoretical physicist Stephen Hawking predicted that black holes aren't entirely black. They should emit faint radiation due to quantum effects near the event horizon. This Hawking radiation would cause black holes to slowly evaporate over extraordinarily long timescales. Though too faint to detect with current technology, this prediction has profound implications for physics and information theory. Impact on the universe. Black holes aren't just cosmic curiosities. They play crucial roles in shaping the universe. Supermassive black holes at galactic centers influence their host galaxy's evolution, regulating star formation through powerful winds and jets that push material away. The relationship between a galaxy's size and its central black hole's mass suggests they grow together through complex feedback mechanisms. When black holes merge, they release enormous amounts of energy as gravitational waves, more power than all the stars in the observable universe combined. Though only for a brief moment, these collisions might have been common in the early universe, contributing to the rapid growth of supermassive black holes. As a conclusion, black holes represent physics at its most extreme. They're laboratories for testing our understanding of gravity, space-time, and quantum mechanics. From stellar mass black holes formed in supernova explosions to supermassive monsters lurking in galactic centers, these objects continue to surprise us with their diversity and behavior. Recent years have brought discoveries that challenge our theories. Black holes feeding faster than should be possible, mysterious intermediate mass black holes beginning to reveal themselves, and second-generation black holes proving that these objects have complex life stories involving multiple mergers. As our observational capabilities improve with gravitational wave detectors, space telescopes, and globe-spanning radio arrays, we're entering a golden age of black hole astronomy. Each discovery brings new questions. How exactly do supermassive black holes form? What happens at the singularity? Do black holes preserve or destroy information? These questions drive cutting-edge research across physics and astronomy. Black holes remind us that the universe contains phenomena far stranger than we ever imagined. Regions where the fabric of space and time is stretched, torn, and fundamentally transformed. And we're only beginning to understand these cosmic enigmas that have captivated human imagination since their theoretical prediction over a century ago. If you enjoyed this journey through the terrifying beauty of space, make sure to like this video, subscribe to the channel, and turn on the notification bell so you don't miss what's coming next.